Thank you for joining us for Dinaburg Technology presentation. We would like to talk a little bit about what we have and what we developed in the last few years. Our goal is creativity, simplicity, innovation, and sustainability. This is our team and leadership. Some of us outside of the industry, but most people you see in this picture, they spend majority of their career in audio industry from different aspects of engineering, product design, acoustic design, and R&D. Our purpose is to enhance a listening experience through science and advanced technology. And our promise is to provide developers of manufacturers and audio products with innovative, scalable solution that delivers clear competitive advantage in terms of sound quality, size, and energy efficiency. What we learned so far, we can bring different benefits to a different type of a products because each driver based on size will deliver different subset of benefits. But in general, the three main areas which come up is the sound quality, reduction in size, energy efficiency, and sustainability. And we will dig into some of them a little bit deeper down the line. Scalability was one of the very important factors we had to prove over the years. We had to validate for the industry that our technology scales, and what I can say today that we have samples of a factory-made headphone drivers, 6.5-inch drivers, and everything in between can be made and produced based on end customer request. When it comes to sustainability, it depends on the product. It's a very interesting aspect, but the simplest one I can bring in mind, let's say in case of 6.5-inch speaker, our design allows to install it in 2.6 liter volume, which brings roughly 25 to 30% reduction to a traditional box size you would utilize for the speaker of that size. And that's where sustainability becomes important. You're using 20% less materials to make enclosure. You have to use 20% less material to do packaging. You can put 20% more of that product into your container as you're shipping it, and you require 20% less storage once that container arrives here or any destination where the product is sold. And the last step of that will be as the product gets shipped to consumer, because you have a reduction in overall weight, you have to pay less for the shipping. And the very last step comes in when the end of the life of product occurs, because we're physically using less material, it means there is less material have to be recycled at the end. Evaluation of speaker design. This is how we see where we at and what we did. Originally, when Rice and Kellogg invented the speaker, it was a speaker in a seal box, and that's what been used and utilized till probably late 40s, late 50s. Around 50s, the industry figured out if we're going to install the port somewhere in the system, we can squeeze some additional benefits which we did not have before. After the port, the industry figured out, okay, what if we need to have a completely sealed enclosure, but we still would like to get the benefits of the port? They implemented the passive radiator approach. The passive radiator delivers some of the benefits of the port, but it's never installed in a plane where the sound is generated and sent towards the user. What my dad ended up doing due to the physical improvement and the concept work he did, in the simple terms, he took the passive radiator and he married it to the active driver in a concentric coplanar assembly. And that concentric coplanar assembly delivers benefits you cannot achieve any other way. This diagram shows what actually happens to the system. The way we interpret what we have in three ways. Traditionally, any traditional transducer generates sound and pistonic motion, and only 50% of that energy is sent towards the user. That's those red arrows we see. The other 50% is set into the enclosure, and depends if you're using a port or passive radiator in traditional design, only 20 to 30, maybe 35% of that energy gets converted into usable sound. In our design, we're able to take all of that energy and convert it into usable sound. And the third energy comes in play, which is energy B. That's kind of the most important energy, typically not captured, and creates a lot of problems in audio reproduction. This was the original concept work which my dad used to build the transducer design. This work is based on a simple law of physics called PV equal constant. PV equal constant reads that pressure, velocity always should stay stable. Imagine this, S right here, it's your surface of the active cone, and it moves in H, which is X max of your driver. And your X max will stay the same if we're sitting on the center. Now, in our design, we have an active part here in the center. It says active S1. And to the side of it, we're adding a stabilizer part, which is S2. What occurs, in this case, the active goes up, it displaces the stabilizer. And that displacement, the way it occurs, balances the whole system out. The main goal my father was trying to achieve as the sound lover, he was trying to generate a cleaner sound, a better sounding sound. And based on his thought, he realized that if we can create the most optimal environment in this area right here, where the speaker actually operates, you can improve the sound reproduction. Because if that air volume and exhalation of the active part stays super stable, then you can generate sound more accurately. Energy B. This is what happens with energy B. The acoustical short circuit, that's the energy we capture as an energy B. In the traditional transducer design, this is the magnet, this is the active cone, and if the cone moves in and out, there is a forces are generated on the frontal area and on the back side of the cone due to the movement. When that speaker physically sits in the box, that energy from the forward pistonical movement and from a back pistonical movement start hitting the walls of the enclosure. That's why we see in the last 20 years kind of a fundamental change in the speaker design. They went kind of from more being a square to being more like a narrow columns. And what that does, it allows that energy versus hitting the enclosure of the box to physically escape on the sides of the box. And it's just bypassing that enclosure. And that's why even a lot of enclosures been smoothed out where that energy kind of escapes them. What occurs in concentric coplanar design, we have an extra surface which is capable of absorbing that energy when it's generated due to interaction between two surfaces. And when the time comes, that energy actually can be released as a positive sound energy towards the listener. And that's the energy B, which we are able to capture and convert into the usable sound. Pretty much in our case, every shred of energy generated by active portion of the motor structure is converted in some type of a usable energy or sound, and we don't have to fight with it because the way the system is designed, it's constantly balancing itself. To show that, this is a 6.5-inch speaker. We're using a strobe light, which is generating 76 hertz per second frequency, and the speaker is actually generating 75 hertz continuous tone. And what this does, it allows us visually see 1 frame per second interaction. This is a general design of the driver. Everything we have is traditional, conventional components. Any type of materials can be used in our driver design. In general, our driver is what any factory is producing today. One is a traditional loud speaker. Two is a traditional active speaker cone surround. Two on outside is also traditional speaker cone surround. Four is a frame. And three in this case is Concentric Coplanar Stabilizer. And you kind of can see the same design from the back. We have the same design. It's open like any other traditional speaker. Magnet structure based on a need of the performance and the material cost the customer wants to invest. And the last thing depends on the design. We have what is called a PSR ring. It allows us to control the environment inside of the enclosure a little bit better based on the implementation of the driver. This is the console work which was done in 2023 and the work which was presented at AES. What we had to do in console, we built two models. The one on the top is the C2S alignment, 3-inch driver in the middle, 6.5 inches overall. And on the bottom, you see identical 3-inch driver in a traditional alignment where there's that identical amount of surface area, material, surrounds in a traditional passive radiator. The only difference is sitting on the back like any traditional passive radiator would. And the difference is what we see between those lines. We get an extra boost in lower frequency, and then you get an extra performance in the vocal range of a driver performance. CanJam is the headphone show, and we would like to present what we did for headphone industry as a reference design. This is our attempt for a high-performance headphone driver. It's a 60 by 72. At the core, it's your traditional 40 millimeter active, but OD overall 60 by 72. It's a little bit unconventional, but fits perfectly fine in any headphone design because it's an oval shape which is used by all headphones regardless. The key benefits of this design: low distortion, better phase linearity, and manageable group delay. What is the benefits of this driver for headphone industry? This is a driver as a system where we flatten it out to see how well it performs. We brought it to about 90 dB, and we start pushing it by 5 dB increments to see when the compression will onset on the device. What we realized once we pushed it to 115, we did not saw any compression. Compression truly started coming in at 118 to 120 dB, depends where you look at the frequency range. Most people never will listen anything above probably 100, maybe 105 dB. What this allows to do for headphone designers to have a extra headroom in case of ANC application when you need to cancel extremely loud sound which comes in abruptly, but you don't want to operate at those levels at any given moment. This is the phase response of the same driver. This is this is how data came out. It's the same data we've seen on a previous chart, except exposed one on top of each other to see how much deviation we get in phase as the driver pushed louder, louder, and louder. Pretty much, there is almost no deviation in phase the louder the driver plays. Where this becomes important when we try to apply internal time difference, IATD, because our hearing was developed in caves over millennia. We're very sensitive to phase linearity and sound reproduction. And the bigger that phase differential, our ears, when that sound hits them, will hear different things. Okay, haptics. Due to its natural design, we're able to produce a lot of lower frequency. And that's one of the benefits what this technology can do. If a company is specifically looking to install something like a lower frequency shaker in their device, it's not longer required. You literally can use driver to generate super low frequencies, which actually felt through the headphone as the playback occurs. Other benefit we discovered for active noise cancellation have to do with the phase. In traditional transducer design, in order to deal with the phase issues, typically you have to build what is called LRC phase correction network into the logics of the electronics to help correct the phase issues of the driver. In our case, because that phase is so tight, that entire section of components, when assembly of the driver occurs, most likely can be removed altogether. And it goes back to efficiency and saving on items which not required. This is a more traditional phase response curve, which is also super important in noise cancellation. Traditionally, industry accepts that the phase can be plus minus 90 degrees in order to be able to do noise cancellation. In our case, we can keep plus minus 35 degrees from 40 to 5,000 hertz at 110 dB. And pretty much this is the region we're looking at, like right here. Typically, 1,000 to 2,000 hertz would be traditional approach, and then it spikes up. In our case, we can take it all the way to 5,000. Same thing, this goes towards the noise cancellation. The higher you can push your driver without the compression, the higher noise levels you will be able to cancel, because you're physically able to generate those higher, louder sounds as they captured by electronics in order to truly cancel them out. This is an interesting slide. This is a THD performance of the driver under load. We were generating about 100 dB of SPL. We get less than 3% distortion at 50 hertz, and then from 200 hertz to 10,000 hertz, you get 0.2% distortion from the driver. And that's already set up as the system where we have to overcome the cushioning, the back volume, the housing, and everything what goes into building the final product. The benefits of a deep bass response is kind of, this is mainly like lower frequencies right there, and it's the same approach. Like if you can generate louder and higher sound, you can generate a cleaner and deeper bass at the end of the day. Lower distortion, better control of THD, IMD, and TIM, which is transient intermodular distortion. I never can pronounce this one, sorry. Better phase response, and the better phase response actually helps to improve DSP or EQ issues. You need to do physically less of it, and it can be done faster. We can improve the human speech intelligibility because the driver, when it interacts with air, physically generates cleaner sound because there is less distortion when it's movement and an interaction of active part with the air occurs. And the last one is probably depends what type of a product is made, because design overall more efficient, it delivers more energy efficient product. And that can be a double-edged sword. Somebody can simply say, my final product can last 40 hours on the battery, or you can put a smaller battery and you can say, my product lasts 20 hours. Pretty much it's up to the final product designers to determine how they want to use the benefit. I think that's it. That's all I had. Any questions? Yes, sir.
What can my consumer listen to? I mean, comparing that to a conventional driver, would my consumer tell the difference?
Yes, your ear will be able to tell a difference. Cleaner sound, more pleasant sound. And then it's all going to be, if you want more bass, we can give you more bass. If you want to have from a consumer perspective, what kind of product we're talking about?
Any type of consumer speaker, like, does that efficiency translate to just better tone control, or is it louder, or what?
Good question. Due to less noise generated during the actual sound reproduction, that sound to all the people who listen to the product to date sounds cleaner. It's almost like if you think about the less noise in a sound wave, which your brain need to kind of comb through and filter through, the better it kind of interprets that sound. But at the same time, the cleaner that sound, it also will sound louder to you. Thank you for joining the presentation, and have a wonderful CanJam show, and have a wonderful day.